Our universe is a vast and mysterious place. It's filled with billions of galaxies, each containing billions of stars. But where did it all come from? How did this incredible tapestry of cosmic wonder begin? The answer, most scientists believe, lies in an event called the Big Bang. Imagine a time before time existed. Imagine a place where space itself was compressed into an infinitely small point, a singularity. This singularity contained all the matter and energy that would ever exist. Then, about 13.8 billion years ago, something incredible happened. This singularity began to expand. It wasn't an explosion in the traditional sense, like dynamite going off in an empty room. Instead, it was the expansion of space itself, an inflation so rapid and powerful that it boggles the mind. From this infinitesimally small point, our universe was born. What caused this sudden expansion? What existed before the Big Bang? These are some of the most profound questions in science, and we're only beginning to unravel their secrets. The Big Bang wasn't an explosion space, it was an explosion space. Imagine the fabric of space itself stretching, expanding in all directions simultaneously. In the first fraction of a second after the Big Bang, the universe underwent an extraordinary period of inflation. This wasn't just a gentle expansion. This was a period of exponential growth, where the universe ballooned in size at an unimaginable rate. During this inflationary period, the universe went from smaller than an atom to the size of a grapefruit, in less than a trillionth of a second. That's fast. This rapid expansion helps to explain why the universe looks remarkably similar in all directions, a feature that had puzzled astronomers for decades. The first 10 to the minus 43 seconds after the Big Bang constitute an era known as the Planck epoch. This period is a mystery shrouded in the language of mathematics. During this incredibly brief sliver of time, the universe was so hot and dense that our current understanding of physics breaks down. The four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, are thought to have been unified into a single force. Trying to describe what happened during the Planck epoch is like trying to read a book with pages ripped out. We can see the edges, the remnants, but the full story remains elusive. Our current theories simply aren't equipped to handle the extreme conditions of this early universe. To understand this period, we need a new physics, a quantum theory of gravity, that can reconcile the large-scale structure of the universe with the strange world of quantum mechanics. As the universe expanded, it cooled. And as it cooled, energy began to condense into matter. This wasn't the familiar matter of atoms and molecules, not yet. Instead, it was a seething soup of exotic particles, things like quarks, leptons and bosons, the building blocks of the matter we know today. Imagine a cosmic dance floor filled with particles colliding, annihilating and being created anew. This early universe was a hotbed of activity, a particle physics experiment on a grand scale. As the temperature dropped further, these fundamental particles began to stick together, forming protons and neutrons, the familiar particles found in the nucleus of every atom. This era, known as baryogenesis, is crucial for understanding why our universe is made of matter and not antimatter. It's a mystery we are still trying to solve. Section 5. The first elements, from a sea of particles to the building blocks of stars. About 3 minutes after the Big Bang, the universe had cooled enough for protons and neutrons to combine and form the first atomic nuclei. This process, known as Big Bang nucleosynthesis, is a cornerstone of the Big Bang theory. During this period, the universe was like a giant nuclear reactor, fusing protons and neutrons into the nuclei of the lightest elements, hydrogen, helium, and trace amounts of lithium. This process was governed by the delicate balance between the expansion of the universe and the strength of the nuclear force. Too fast an expansion, and the universe would have been filled with only hydrogen. Too slow, and all the hydrogen would have fused into heavier elements, leaving no fuel for the stars to come. Section 6. Echoes of the Big Bang, the cosmic microwave background. The Big Bang model predicts that the universe was initially incredibly hot and dense. As the universe expanded and cooled, this heat should still be detectable today, albeit at a much lower temperature. In the 1960s, astronomers Arno Penzias and Robert Wilson stumbled upon this faint afterglow, a faint hiss of microwave radiation coming from every direction in the sky. This cosmic microwave background radiation, or CMB, is the oldest light in the universe, a snapshot of the universe as it was just 380,000 years after the Big Bang. It's a baby picture of the universe. By studying the tiny fluctuations in the temperature and polarization of this radiation, cosmologists can learn about the early universe's density, composition, and geometry. The CMB is a treasure trove of information about the early universe, and it provides some of the strongest evidence in support of the Big Bang theory. In the 1920s, astronomer Edwin Hubble made a groundbreaking discovery. He observed that galaxies are not stationary but are moving away from us, and the farther away a galaxy is, the faster it is receding. This observation led to the development of Hubble's law, which states that the velocity at which a galaxy is moving away from us is proportional to its distance. This observation of an expanding universe is one of the key pieces of evidence supporting the Big Bang theory. It suggests that the universe was once much smaller and denser, and that it has been expanding ever since. Imagine baking a loaf of raisin bread. As the bread rises, the raisins move farther apart from each other. Similarly, as the universe expands, the galaxies within it move farther apart. The Big Bang model predicts the relative abundance of light elements in the universe. This prediction is based on the idea that the early universe was hot and dense enough for nuclear fusion to occur, but only for a short period. The model predicts that roughly 75% of the universe's mass should be hydrogen, about 25% should be helium, and trace amounts of lithium and other light elements should also exist. These predictions have been confirmed by observations of the abundance of light elements in stars, galaxies, and the interstellar medium. The close agreement between the predicted and observed abundances of light elements is a remarkable success of the Big Bang theory. The Big Bang theory is one of the most successful scientific theories ever developed. It provides a comprehensive framework for understanding the origin, evolution, and large-scale structure of the universe. It explains the expansion of the universe, the cosmic microwave background radiation, the abundance of light elements, and the formation of galaxies and stars. The theory continues to be refined and tested as new observations and discoveries are made. It has profoundly impacted our understanding of the cosmos and our place within it. The Big Bang theory is a testament to the power of the scientific method to unravel the mysteries of the universe. While the Big Bang theory has been incredibly successful in explaining many features of our universe, it also leaves some profound questions unanswered. What caused the Big Bang itself? What is the nature of dark matter and dark energy, which together make up about 95% of the universe's energy density? Is our universe unique, or are there other universes out there? These are just a few of the mysteries that continue to fascinate and challenge cosmologists. The quest to understand the universe's origin and evolution is an ongoing journey, and the Big Bang theory provides the foundation for this grand scientific adventure. The universe is full of wonders, and the more we learn, the more we realize how much more there is to discover.